Swayam Prabha. Digital India. Educated India.
Let us begin with phase equilibrium, and one of the central issues of the theory of phase equilibrium is the phase rule. So we would like to discuss this phase rule from some basic standpoint. And let us to start with, we just take note of one component system first. So we begin with one component system like an ideal gas, and so I consider in one component system, say an ideal gas or any gas in a volume V at a temperature T under pressure P. And we know that it satisfies an equation like PV equal to RT if we take 1 mole. So what does it mean? That if I have a volume V, then if I know the volume and temperature, I can determine P. So out of the 3 variables, I can actually work with 2 independent variables. So even if there are 3 variables like volume, pressure, temperature, 2 variables are sufficient to describe the state. State means in terms of an equation of state. So I have three variables are pressure, volume, temperature, and but this equation acts as a condition or a constraint over these things. Means if I know this equation, that means under this constraint I have only 2 variables. That means only 2 free variables. So one constraint is the equation of state. So equation of state is a constraint for this. So I have one constraint and we have 3 variables. So number of free variables by which you can manipulate the system is 2. So number of free variables, I call it the degrees of freedom, is 3 minus 1, number of constraint 1. So 3 variables and 1 constraint, that is equal to 2. So the number of free variables are basically is just 2. Now this is the first case. Now we consider the second case. Now the system, say the gas, we are under such a temperature and pressure that gas is liquefied. If the gas is liquefied and it is in a 2-phase system, then I have it was just a simple gas. Now we have a 2-phase then gas in contact with the liquid. So you now consider the gas in contact with with its liquid. This means what? That means if they are in equilibrium, it is also in an equilibrium condition. Otherwise I could not have used this equation. So gas is in contact with a liquid and under equilibrium. This means that I have chemical potential of in the gas phase is equal to the chemical potential in the liquid phase for the component. Say component is 1, so component is say ith component. So this means what? This and this mu and mu is a function of T and P. Mu is a function of T and P. Then I have so this actually acts as a constraint. Now we have two variables T and P. So now we have two variables Tp and one constraint, that is the equilibrium condition. This equilibrium condition gives me another constraint. So that means that for if mu is a function of T and P, it is another mu for the liquid is a function of T and P, then this automatically fixes that if I fix my temperature, P is automatically fixed. That means we have two variables and one constraint. So number of free variables, that is the degrees of freedom. Again, I am repeating this thing, degrees of freedom. 2 minus 1 is just 1. It is a 1 degree of freedom system because I can only manipulate pressure and not other things, because temperature is automatically fixed because of this equilibrium condition. Now we come to the another example. Say a gas liquid, one component but three phases. The gas liquid, say this is a solid, there are liquids and gas. So if this is a situation, so it means I am at the triple point. So at the triple point, we have equilibrium between the gas, liquid and solid. So I have two conditions, mu at temperature Tp for the gas is equal to mu Tp liquid. Then I have another condition, mu liquid Tp equal to mu solid Tp. So I have two equations, and mu is a function of T and P for the gas phase, mu is a function of T and P for the liquid phase. So this is an equation. This is another equation where we have two variables, two unknowns, T and P. So if you solve it, then it has a unique solution. So this gives an unique solution, and unique solution for TP. That is a triple point. Basically, that indicates a triple point. So now it means we have the number of variables. So number of variables, we have independent variables TP, and number of constraints are basically these two equations, basically two equilibrium conditions. So number of variables, so basically is 2. Then the number of constraints is also 2. So number of free variables or degrees of freedom, that means you can freely choose your system to manipulate the equilibrium, that is equal to 2 minus 2 equal to just 0. So you cannot manipulate the system itself. It is a unique point for the substance itself, and that is a characteristics of the compound, the triple point. So it means that we have, so this is a situation that we have illustrated only with one component, purely by taking care of the number of variables and the number of constraints. If we now generalize this idea for multi-component systems, say I have more than one component, say when I am considering a reaction in multi-phase. So a reaction in a multi-phase system, it means you have several phases and several components. So for multi-phase system and multi-component system, you need to generalize and try to find out how many degrees of freedom are there by which I can manipulate the equilibrium. So the question is, if we try to find out how many degrees of freedom are there in a multi-phase multi-component system, so that we can manipulate the equilibrium condition. So how many degrees of freedom are there in a multi-phase multi-component system, so that I can manipulate the equilibrium condition? So that's the question. And answer is the phase rule, Gibbs phase rule. Let us try how can we actually arrive at this rule, why it is a rule, and it is a most general thermodynamic rule, and we can use it for different situations. So let us come to that. So what the phase rule is. Now suppose I have C number of components. Suppose we have C the number of components or species. and P number of phases. So, and also the system is at temperature T and P. There are two variables. So, how many variables of the systems are there? So the thing is this, say I have component 1. So if I write down the components and the phases, so say I have the one component 1, 2, 3. I have C number of components, and it is again 1, 2, 3, C number of components. This is for alpha phase. Say this is for beta phase. If we go on like this, so we go up to P number of phases. P, note that it is not Pth phase, but P is a number of phase. The C is a number of components. So it is the P number of phases. So it is 1, 2. So this means how many such variables are there? So number of variables is C into P, and we have the temperature and pressure. So if we include temperature and pressure plus 2, that is the number of variables is equal to C into P, Cp plus 2 for temperature, pressure. They are variables. So this is fine. Now let us check how many constraints are there. So the number of variables, I can find out that it is Cp plus 2 is the number of variables. Now how many constraints are there? Number of constraints. Now I can see that I have the variables, say for variables 1, 2, 3, it can be in the alpha phase or it can be in the beta phase. And so what we can do, we see that for alpha phase, so for alpha phase, I have x1 plus x2 plus xc equal to 1, where x are basically the mole fractions. So in the alpha phase, I have the component 1 with the magnitude, with the amount x1 mole fraction, it is x2 mole fraction for the component 2, xc. Not that all components has to be present, some of them may be 0, doesn't matter. But so this is for alpha. And for beta, you have the same thing, x1 plus x2 plus xc. So that is equal to another. So in this way, we go up to P. So it is x1 plus x2 plus xc, and that is equal to 1. So for each equation, is a constraint. So how many such constraints are there? I have, this is for 1, this is for 2, and this is for the alpha phase. So P into number of equations are there to conserve the components in each phase. It is some kind of conservation for each of these phases. So this is the P is the number of equations that, so P number of equations are there. Now we see another thing, that how many equilibriums are there. So how many equilibrium conditions are to be satisfied. We consider a general one. Say I assume that mu1, that is mu1 equal to, or mu alpha for component 1, say for component, I write the components here. For component 1, I have alpha 1 equal to mu alpha for one component, for one, this is for the beta. So alpha is equilibrated with the beta phase for the component 1, mu 1 gamma equal to, then we go up to alpha, beta, gamma, I must go up to mu of p phases for the component 1. So how many such equilibrium conditions are there for one phases? So we have 1, 2, 3, so they are in between. So it is p minus 1 number of equilibrium conditions are there. This constitutes 1, this constitutes 1. So we have, so in between I have the how many equal signs are there, that is p minus 1. So p minus 1 equilibrium conditions for 1, p minus 1 equilibrium conditions are there for one component. So you have the component 2 exactly same way, that is 2 alpha equal to mu 2 beta equal to mu gamma 2 equal to, you go up to mu 2p. So in this way you go up to C number of components. So for the C number, it is again, it is for C alpha equal to mu beta C equal to mu gamma C equal to mu p C. So how many such components are there? I have C number of components. So C for C number of components P minus 1 into C is equal to number of equilibrium conditions. So the number of constraints is P number of equations that conserve the spaces for each phase. So you have P number of equations, and here you have C into P number, C into P minus 1 number of equilibrium conditions. So the total number of constraints or restriction in the system is basically, how many are there? It is P plus P plus P minus 1 into C. That is the number of constraints. And how many is the number of free variables? So number of free variables or number of variables total, that's equal to CP plus 2. So I know how to calculate the number of degrees of freedom for manipulating my equilibrium condition. So therefore number of degrees of freedom we call it F. F is basically the Cp plus 2 minus P plus P minus 1 times C. So this is a simple algebraic. So you have algebraic equation means Cp plus 2 minus P minus Cp minus plus C plus C. So this is the equation. So Cp and Cp cancels out. We have a very simple equation that F equal to C minus P plus 2. And that is called your phase rule. So it means that if you have C number of components and if they are distributed in P phases, then the number of degrees of freedom in the system by which you can manipulate the equilibrium is basically F equal to C minus P plus 2. So that's the simple argument that. But this is a very tricky thing that one must remember. And also what we have not taken into account are the number of reactions. If the reactions are there, they are special cases and they are also constraints for the system. So those constraints must be taken into account. But this is for purely non-reactive situation. And now we check it for the cases that we already discussed. Say in the case of one component system, we now take that for one component system, this reduces to, so F equal to 3 minus P. So this becomes more simple. And for one phase you have two constraints. You have for 2 degrees of freedom. For one phase, for P equal to 1, for ideal gas case, F equal to 3 minus 1 equal to 2, that we already actually discussed in the starting of my class, that is the number of degrees of freedom is 2. So that actually comes into from this equation for one component equation. For P equal to 2, gas in contact with vapor, gas in contact with liquid, that is in two-phase situation, we have F equal to 3 minus 2 equal to 1. That we also discussed when we began with this discussion. And for the triple point, you have 3 phases. for the triple point, if basically 3 minus 3 phase, that is 0. So we have no free degree of freedom to manipulate the equilibrium system. So that is the very interesting situation, and we can show that for any thermodynamic system which has several phases and several components, so they can be used in this formula, in this particular rule, to find out the number of components or the number of degrees of freedom by which I can actually characterize my equilibrium. So that is the Gibbs phase rule, and it actually is a central point in the phase equilibrium. So with this I close, and thank you all for your kind attention.